This section is about circular motion and gravity. Imagine that you're orbiting a planet in a circular orbit in your spacecraft. You're doing it because of the force of gravity. The force of gravity is pulling you towards the centre of the planet. So why don't you fall towards the centre of the planet? What's going on here? Before we answer these questions, let's step back and think about forces in general and gravity specifically for a minute. First, what is gravity? Gravity is a force between two objects that have mass, i.e. that are made of stuff. How big the force of gravity is depends on four things. The masses of the two objects, in our case the mass of the planet and the mass of the spacecraft. It depends on the distance between two objects. The force is proportional to 1 divided by the distance squared. We call this an inverse square law. And the last thing it depends on is a number, called the universal gravitational constant, big G. Big G is equal to 6.67 times 10 to the minus 11 meters cubed per kilogram per second squared, i.e. it's really, really small. This means that one of the masses needs to be really big, or the distance between the two masses really small, for the overall force to be big enough to notice. Second, what are forces? And what other ones are there apart from gravity? What are forces is a big question, and we'll talk about forces many times in this course. But put simply, a force is something which causes an object to change how fast it's going or the direction that it's going in. Important for us studying classical mechanics is there are only three fundamental forces, and that means only three things which cause forces. These are gravitational, which is attraction between objects with mass, electromagnetic, which is attraction between objects with electric charge, and nuclear, forces which hold the inside of atoms together. Only two of these forces are important in classical mechanics: gravitational and electromagnetic. Electromagnetic, also known as electric contact forces, are experienced as repulsive forces when atoms, for example surfaces of objects, are in close contact. We'll come across these as reaction, friction, tension, and compression. Back to our orbiting spacecraft and why it doesn't fall towards the planet's surface. Well, the short answer is, it does. We've said that force is due to gravity and directed towards the centre of the planet. Now we need one of the most important laws of classical mechanics, Newton's second law, which says that force is equal to mass times acceleration. So if the force is directed towards the planet's centre, then the acceleration is also directed towards the planet's centre, and the spacecraft must move towards the planet's centre, which it does. The two crucial things here are, one, that the velocity is not directed towards the planet's centre, it's at right angles to the gravitational force, and two, the velocity is exactly the right value so that when the spacecraft is accelerated towards the planet in the direction of the gravitational force, it's also moved away from the planet because of the original travel at right angles to that force. The combination of these two means that it's still the same distance away from the planet, but moving round in a circle. An interesting fact is that a given rate of completing an orbit corresponds to a given distance away from the planet's centre. This means that geostationary satellites which orbit at the same rate as the Earth rotates, i.e. ones that are always looking at the same part of the Earth's surface, have to be 37,000 kilometres above the Earth's surface. Because they're so far away, they actually have very poor resolution, but they can see a wide area of the Earth's surface. In contrast, polar orbiting satellites have an altitude of only 850 kilometres and orbit the Earth many times a day, viewing all locations on it. They're nearer, so they have much better resolution, but they only view the same location twice per day instead of all the time. Finally, what happens if you're travelling at a different velocity to the exact one needed to stay in circular orbit? If you're travelling too fast, you'll fly off into space on a hyperbola. If you're going too slowly, you'll fall towards the Earth on a parabola. In summary, a circular orbit is just a special case of many different paths that a planet's gravity can make you take. Gravity is a force between objects with mass. It's what keeps things in orbit.